Hello everyone. We're going to continue chapter 2 with section 2.2, and as I mentioned several times in the last section, we're going to be doing graphing in this section. And so our learning objective for this section is we want to learn to represent data from those frequency distributions that we did in section 2.1 graphically, and we're going to use 3 different types of graphs. However, it ends up actually being 6 different types, but the main types are histograms, frequency polygons, and ogives. Okay, so those are our 3. So we have histograms, we have frequency polygons, and we have what are called ogives. I know that looks like ogive, but it's pronounced ogives. Now, why does that make 6? Well, that's because for the histograms, we're going to have histograms that are frequency histograms. And remember, that's where you have the actual numbers. So you could say, 12 out of 40 in our study, or you could have what's known as relative frequency. So for histograms, you're going to have frequency histograms and relative frequency histograms. And the relative frequencies are, you can think of it like the percentages, but instead of saying, let's do something simple, like instead of saying 10 out of 40, you would say 25% or 0.25. So frequency would just say there's 10, and relative frequency would say there's 10 out of 40, or 0.25 of the data was from that specific class. So for histograms, you have both of those. Then you have the same thing when you go to frequency polygons. So frequency polygons are a different type of graph. And for those, you also have regular frequency polygons, and then you also have relative frequency polygons. And then the last type are the ogives, and the same with that. There's frequency ogives, and there's relative frequency ogives. And so because of that, we actually end up with 3 main types of graphs, but each of them have 2 subcategories. So just to kind of give us a heads up as to what these different graphs are before we get into the details, I'll just kind of give you a little bit of a heads up. Histograms are a type of bar graph, a specific type of bar graph, but histograms are going to look like a bar graph. Okay, they're going to have bars that represent the different classes, the frequencies or the relative frequencies for the different classes. A frequency polygon is going to be a type of line graph. So instead of having bars, I'll do one that kind of replicates this one. Instead of having a bar that's up that high, you would have just a dot. And then you would have a dot. And then you would have another dot. And then final. And then you would connect those and make a line graph. And then we actually connect that back to the beginning, or back to the x-axis on both sides. We'll talk about how to do that, of course. And then ogives. Ogives used to be called cumulative frequency polygons. I'll tell you why I don't think they're called that anymore when we get to them, but basically an ogive is where you are listing the cumulative frequency. And so because you're listing the cumulative frequency, ogives can only go upward. Whoops, that didn't go the way I meant it to. So ogives can either, they always start at 0 because that says that's like the starting place when you don't have any data. And then remember, in cumulative frequencies, we're adding everything up as we go. So how many is from this class, the upper bound of this class, and below. And so the only thing ogives can do is go upward or stay steady. They cannot go downward. So ogives will go up until they reach the total number. So for instance, with the one we just gave, if you had 40, an ogive would end at 40. So ogives are again another type of line graph, but they only go upward, or they could stay flat if there's nothing in a particular class. So that's just a really quick highlight of what's coming, and now we'll get into the details. So as we mentioned, the three most commonly used statistical graphs all represent a frequency distribution, so the tables that we made in the last section, visually. Okay, so as we mentioned, we have a histogram is a graph that displays the data using continuous vertical bars, so it's a type of bar graph. A frequency polygon is a graph that displays the data by using lines that connect the points. And then the cumulative frequency graph, again, this is the old term for it, or ogive, is a graph that represents the cumulative frequencies. So again, gathering up how many we have from the upper boundary of that class backwards to the lowest class. So we're going to talk about just the general procedure for creating statistical graphs. It's similar for the three graphs, but there's some little details that you have to change, of course, because they each represent something a little different. So the first thing you're always going to do is you're going to draw and label your x and your y axes. Okay, so you're going to label along here, you're going to label, and then along here you're going to label. This is often labeled with frequency. It'll be something frequency. It'll say frequency or relative frequency or cumulative frequency or relative cumulative frequency. Sorry, it's really hard to draw sideways on this. But this would be labeled with some sort of frequency. And then down here, you're going to have some sort of labeling for the classes. Okay, so we do a little bit differently, whether it's a histogram or a frequency polygon or an ogive, and it tells us here these are the differences. So on the x-axis, we're going to label the class boundaries if we have a histogram or an ogive. Now remember, the boundaries are the ones that don't have a gap between them. So for instance, if you had a class that went from 20 to 24, your boundaries would be 19.5 to 24.5. Okay. For the frequency polygon, you're going to do the midpoints. So you're going to label the midpoints on the x-axis if it's a frequency polygon. And so if your class, let me mark this up here. So this would be for a class of 20 to 24. Okay. And then for the frequency polygon, we're not going to use these boundaries, and we're actually not going to use 20 or 24. We're going to use the midpoint. So in this case, the midpoint from 20 to 24, if we average, 20 plus 24 would be 44, divided by 2 would be 22. So the midpoint in that case would be 22. So for that class, we would use the midpoint of 22. We wouldn't use the boundaries or the upper and lower bound, or upper and lower limit for the class. We would use the midpoint. And that's the difference between the three. And then once we've got that x-axis labeled, we're going to plot the frequencies for each class and draw either the bars for the histogram or the lines for the frequency polygon and ogive. So again, we're just kind of trying to give a heads up to what's coming. And so now let's actually do some examples. So I'm going to recreate this off to the side, even though it's completed here. and that way you can kind of see the process. So they've already given us our frequency table. This is the same table that we had in the, no, I guess it's not. This is the record high temperatures for 50 states. And so they have class boundaries from 99.5 to a 101.5. Remember, that means that the class would be 100 to 104. And then they continue down. So they have all our class boundaries listed. They have the frequencies for each class listed. And we're going to start off by making a histogram. So the first thing that we have to do is we're going to, sorry, it's hard to draw straight on this application. Okay, so we're going to label the side first. I find that a little easier because this is a little easier to see. So the frequencies go as high as 18. You need to look for the largest number that you have, and in this case it's 18. So that means that our y-axis here needs to get as high as 18. So I'm going to, again, try to do my best to write sideways here. So we've got frequency over here, and we need to get to 18. And so you pick a reasonable number. Now they picked 3s. I'm going to go ahead and pick 2s, just so you can see that it really doesn't matter. But somehow we need to label this y-axis so it gets up to at least 18. So I'm going to go ahead and label mine with 2s. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay? And then along the bottom, if you remember from the prior slide, it says for histograms, we're going to label the x-axis with the class boundaries. And so I'm going to start my first label down here at 99.5. I'm going to go every 2 squares here just so I have enough room. Otherwise, I think I won't be able to fit it in. So 99.5, and then I'm going to do 104.5. And then I'm going to do 109.5 and continue. So 114.5, 119.5, 124.5, and 129.5. And then my last number, the upper boundary of my last class, is that 134.5. Okay, so I label those along the bottom. And then between each of these, I put what the frequency is. So between 99 and 104.5, I have 2 values. And so I'm going to make a bar that goes between 99.5 and 100.5 and make a bar. Now, they usually in the book will color theirs in. I'm probably not going to color ours in because it just gets kind of sloppy looking. So again, we're going to make that bar that comes up and over between 99 and 104.5. All right, and then we're just going to continue. So between 104.5 and 109.5, our frequency is 8. So we're going to take that up and over and make a bar between 104.5 and 109.5. Boy, my lines don't look very good. Okay, and then we're going to go and just continue that. Our next one is 18, so we need to go all the way up to here, and you notice that the bars touch. Okay. And then we have 13. Now that's between, we have 12 and 14 marks, so we're going to go halfway between 12 and 14. And then 7 from 119 to 124. And then 1 for the last two classes. So that's not even up to this first bar. That's only, this was marked at 2, so we only want to go up to 1. And then what's nice about this is this gives us a really nice visual of what's going on with the data. So the data kind of starts out low, climbs fairly decently here, but then the biggest number of states are definitely in these two categories, and then it drops back down on the other side. So it's kind of symmetric, other than there's a couple, there's 2 in 2 different classes down here rather than 2 in just a single class, but it kind of peaks in the middle and then comes down on each side. And so you can see that really visually. I mean, as people really like visual representations. There's a reason that there's the statement or the saying that a picture's worth 1,000 words. I could explain to you, if you've never seen the Eiffel Tower before, I could explain to you what the Eiffel Tower looks like with, 1,000-word essay. About how it's wider at the base, it's made out of metal, it comes up to the top. There's a way that you can, stand on different levels of the Eiffel Tower, all kinds of things. I could list all kinds of things, and you still wouldn't really understand what the Eiffel Tower looked like. But if you saw a picture in almost an instant, you would understand what the Eiffel Tower looked like. So this graph is a mathematical representation of this data, of this frequency table, of this frequency distribution. And so we can see pretty clearly how it's distributed. Okay, so now what we're going to do is we're going to take that same data and we're going to represent it with a different type of graph with the frequency polygon. So in order to make the frequency polygon, we have to have the midpoints for these classes. And so in order to calculate those midpoints, if they weren't already given to you, so here we have them already, but if you didn't have them already, you would take each of the upper and lower class boundaries and you would add them and divide by 2 to find the average. So the average between 99.5 and 104.5 is 102. The calculation for that one is here. We'll do the next one. So the average of 104.5 and 109.5, the average of those in order to find the midpoint would be, we would total these, which would give us 214, and then divide that by 2, and we would get 107. Now, if you were given the class limits instead of the class boundaries, you could use the class limits. So in this case, for instance, the class limits for this would be 105 to 109 would be the class limits. That would also add up to 214, which then would also give us a midpoint of 107. So you can either use the limits or the boundaries, whichever you're given. Oftentimes with this, we have the class boundaries because we needed them for the histogram. A lot of times on your problems, on your homework, it asks you to do a histogram and then uses the same data. And so a lot of times you have those boundaries already. Okay, and then of course we have the same frequencies. Now I'm going to scooch ahead here. I can't remember if they have the, yes, they do. Okay, so now when we go to graph the frequency polygon, we don't need the class boundaries for the frequency polygon anymore. We only need the midpoints and the frequency. So you don't have to take this off your table, but for the sake of space, they only list in this table the midpoints and the frequencies. So here's all our midpoints that we had from these classes, and then the frequencies. So they're just giving us these 2 columns. Just cutting off that first column and just giving us these 2 columns. Okay, so what next? Well, we're going to do the same thing we did before. We know that we have to get our frequency as high as 18 because that's the largest number in all the frequencies. And so we're going to label our, makes me mad that I can't draw a straight line on this. Okay. So we're going to label our frequencies over here with the twos by twos again so that we can get up to 18. So 2, 4, 6, 8, 10, 12, 14, 16, 18. And again, it wouldn't matter if you wanted to go by threes. I mean, you could conceivably go by fives. I think in this case, that might be a little bit too big because you get pretty wide gaps. But twos or threes in this case would both be fairly reasonable. They went by threes. I'm going by twos, just to give you an alternate view of it. All right, and then along the bottom, we're going to look at the midpoints. So the midpoints start at 102 and continue up by fives up to 132. Now, when you do this, make sure you leave a little bit of space at the beginning because we are going to do something here before the 102. So I'm going to mark the 102. I'm going to mark it here. So 102, 107, 112, 117, 122, 127, and 132. Okay? And then instead of having bars for these, each of those classes gets a single point at its midpoint. So the class, remember the class for this was 100. I'll go back up and show it so you can see it. So remember the class boundaries were 99.5 to 104.5. And then 104.5 to 109.5. So the class limits, the class was, for this one, was 105 to 109. The class for this first one was 100 to 104. So that class, each of these classes, even though it involves, 5 numbers, 100, 101, 102, 103, 104, even though it involves those 5 numbers, it just gets one number or one dot at the midpoint for that class. And so in this case, our first dot is going to be at 102 at 2. And then 107 at 8. At 112 will be at 18. 117 will be at 13. 122 will be at 7. 127 will be at 1, which again isn't even to the first mark because the first mark was 2, so it's only halfway to that first mark, and 132. And then we go back and we connect those dots. If I can get them to connect decently. All right. So there's supposed to be straight line segments between those points. You can see from their pretty graph what it's supposed to look like. Okay. Okay, so we connect those dots, but we're not done yet because the reason this is called a frequency polygon is because we want to make a polygon. So if you think back to geometry class, make your geometry teacher proud. If you recall, a polygon is a many-sided figure made up of line segments, but it's also closed. Like for instance, we wouldn't say that this 3-sided shape is a polygon because it's not closed. If we want to have a 3-sided shape that's a polygon, we've got to make a triangle. And so a polygon needs to be closed. And so in this case, we don't have our polygon closed. We have these line segments up here that are just kind of floating up above the x-axis. And we want there to be a closed figure here. And so what we do, and I don't like that they don't mark this. I'm going to go mark it on theirs. This should be marked 97. And the same thing up here, this should be marked 137. So we go back 5 to the midpoint of the class that was before this that didn't really exist, which would have been 97. And then we go one more class that didn't exist to 137. And the reason for that is because the frequency for that class would have been 0 and the frequency for this class would have been 0. And so we take that 97 and we bring it back to 0. And then the same thing for the 137. We bring that down to 0. And now, using the x-axis and our segments from our frequency polygon, we have a closed figure. We have a closed polygon. I didn't label the bottom. I really should have labeled the bottom here. So this is the temperature, and we should have, labeled the top. So these are record highs, record state highs, something along that. Same thing with the other one that we did up here. I should have record state highs. And temperatures. So that is what a relative or what a frequency polygon looks like. Now remember, we graphed the exact same data. So this graph that we just did and that histogram that we did both represent the exact same data. They're just different ways to do it. Some researchers prefer to use frequency polygons, some prefer to use histograms. They're both completely appropriate. And then lastly, our third main type of graph is an ogive, which, as I said, used to be called a cumulative frequency polygon. When we're done with it, I'll explain why it's not called a polygon anymore. So to draw the ogive, we need to go back to using the class boundaries. Okay, so for the ogives, you need the class boundaries again. We do need the frequencies to calculate the cumulative frequency, but we aren't going to graph the frequency. We're only going to graph the cumulative frequency. So let's talk real briefly about how we get these cumulative frequencies again. Remember that this means we have two values that are 104.5 degrees or less. So we have two states that are 104.5 degrees or less. We have 10 states that are 109.5 degrees or less. That's what the cumulative means. We're accumulating the data as we go. And so if you look back over here, we had 2 and 8, so we have a total of 10 that are in this class or lower. In practice, you can take 2 plus 8 to get your 10. I'm not going to do that all the way down, but if you remember from section 2.1, that's how we did it. So then 10 plus 18 gets us 28, and that represents that there are 28 values that are 114.5 or less, 41 values, when I add in this 13, that are 119.5 or less, and so on. And so our very end one tells us that there are 50 values that are 134.5 or less. And then when we graph, I'll go ahead and cross this out. When we graph, we don't need those frequencies anymore. We need the boundaries and we need the cumulative frequency. So we're going to get our y-axis and our x-axis. But our y-axis is going to be different than it was for those other two graphs, even though this is the same data. Because when we do cumulative frequency, remember, we're adding it all up. So our largest number for our cumulative frequency is 50. So we don't need to just get up to 18 now. We need to get all the way up to 50. So this might be a good time to go by 5s instead of by 2s. Because if we went by 2s, we'd have to, have 25 marks. So I think in this case, I think what I'm going to do is I'm going to mark every 5 and then just label every other one. Okay, so here's 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. And this would be the cumulative frequency. And then this still would be temperatures and this would still be state highs. Okay. Now, how do I label the temperature down here? Well, I'm going to go back and use the class boundaries. So I'm going to start with 99. As far as labeling the x-axis, I'm going to start with the 99.5 again. And then the 104.5, 109.5, 114.5, 119.5, 124.5, and 129.5, and then last but not least our 134.5. But we have to be careful where we start this graph at, because remember this 2 right here meant that there were 2 values that are 104.5 or less. So that value of 2 needs to be at 104.5. So we're using the upper class boundaries to graph these. So I'll underline those all the way down. So at 104.5, we're going to mark 2. So not at 99, but at 104. So at 104.5, we're going to mark 2. Remember, this is 5 and this is 10, so 2 is way down here. We're going to mark 10 at 109.5. At 114.5, we're going to mark 28. We accumulated 28 of the states that are 114.5 degrees or less. 41 that are 119 or less. 124.5 or less, we're in this category right here, this class. 124.5 is at 48. So almost to the top, not quite. So we have 48, and then we have 49, and then we have 50 when we get to 134.5. So 124.5 was at 48, 129.5 was at 49, and then 134 was at 50. Okay, and so what do we do with this first one? Well, you have to kind of think back to our last, to the frequency polygon, and you're going to think as if there was a class before this. So what if there had been a class that was 94.5 to 99.5? What would the cumulative frequency have been? 0, because we didn't have any data that was between 94.5 and 99.5. We had nothing. And so just like the last one, oh, and I forgot to mention, this is really important, I forgot to mention that these are called anchors. Change color here. So this initial spot right here and this final point right here, those are called anchors. They anchor the graph down to the x-axis. Okay, so these are the anchors. And the same thing here. When we do that first point on the ogive, that is also an anchor point. So that's called the anchor point. It holds the graph down to the x-axis. And then just like on the frequency polygon, we're going to connect the dot. And remember that ogives can only go upward or stay flat. Ours goes upwards each time because we don't have any categories, any classes that have 0 frequency, but we do have a couple at the end where it doesn't go up very much because we only have 1s, and so these last 2 classes do not increase very much on the ogive. Now, why don't we connect it over here? Because if we brought this down to 0, we would be saying that when we got to 134, 138.5 to 139.5 that we had 0, and that's not true. We had gathered up everything up to 50. So it doesn't drop back down to 0, it stays at 50. So we don't want to anchor it on this side because it doesn't make sense for the ogive. And that is why I believe that they changed the name from relative frequency polygon to an ogive. Because it's not really a polygon because it doesn't connect back down to the x-axis, and so it doesn't make a closed figure. And just because it bothered me, I once looked up where the term ogive came from because I had never heard it until they started using it for these graphs. And it comes from, I believe, Latin, and then French, and it meant something along the lines of like an increasing curve. So it is fitting in this case to call a cumulative frequency graph an ogive because it is an increasing curve. So now let's look at their, I'm sure, much prettier version of the ogive. And so this is what theirs looks like. Same thing we had. Theirs is just a little prettier than I could get with mine. But hopefully you understand the concept for constructing those. The last thing that we're going to talk about, not the last thing, the next thing we're going to talk about is our relative frequency and cumulative relative frequency. So sometimes, as we mentioned, sometimes we're more interested in the proportion of the data rather than the actual number. So again, we care more that not that it's 10 out of your subjects that are in a certain category, but that the 10 out of 40 is 0.25 of the entire data set. And so we want to put in the graph these proportions or relative frequencies instead of the actual number 10. So remember, proportion are the relative frequencies. And so then they give their own example. It says, for example, if we're trying to compare the distribution ages in 2 different cities with 2 different populations, this is a time that it would be very valid or reasonable to do this. It would be a lot more understandable or able to compare if, say, we knew 50,000 out of 150,000 people in a city. In one city were 25 to 40, and then in another city it was 100,000 out of 500,000. Well, if we just said 100,000 for each city, I'm sorry, I think I gave those numbers wrong. So let's say one city had 50,000 out of 150,000 that were ages 25 to 40. And then another city, say they had 50,000 out of 250,000 that were ages 25 to 40. Well, if we just compared these with the 50,000, you would say, well, this city has the same number of people between 25 and 40 as this city. But you can see that the proportion is much larger in the first city because it's 50,000 out of only 150,000, whereas in this city, it's 50,000 out of 250. So if we gave their percentages and said that the first city was 0.33 and the other city was, so when we divide these, this comes out to be 0.2. And so that gives us a better comparison to say this city had 33% of its population in that age group and this city had 20%. So that's one good example of why relative frequency would be more appropriate in that case than just the frequencies. Now, when we do cumulative relative frequencies, we're using these relative frequencies. So you can think of it as, the proportions, which we could change to percentages. If we're using those values instead of the actual frequency, so the 25.25 instead of the 10 or the 30.33 instead of the 50,000, when you calculate those, you can calculate them 2 different ways and you may get different answers. So what are the 2 different ways? Why can you calculate it 2 different ways? Well, the reason being is you could calculate all of the relative frequencies first, so you could calculate all the decimals values, those proportions first, and then add those up to get the cumulative frequencies. So in this case, you're getting the relative frequency first, and then using those to add up to get the cumulative relative frequencies. Or in this case, you can do the cumulative frequency, so you can take the actual numbers, the 10, and the, you know, take each category's actual frequency number and add those up, and then use each of those first. So you, in this case, you would do the cumulative frequency first, and then switch those cumulative frequencies to relative cumulative frequencies. And because of rounding differences, you may get different answers. And how do you handle that? Well, if it was a test for me, I wouldn't count it wrong either. I would accept it for either way. Sometimes Alex will get a little finicky. So if you know you're doing it correctly, or you think you're doing it correctly, but you're not getting the right numbers, I would suggest you check their example and see what they did in their example. If they did, you know, whichever way they did it in the example, do it that way for your problem, and it should eliminate the problems. A lot of times they try to avoid in Alex having situations like that, so hopefully you won't run across it often. Okay, so in this case, we have a different situation. We have the frequency distribution. I don't know why they're stuck on 50 as a data set, but not all data sets, not all samples have to be 50. They've done a lot of 50s. But this frequency distribution shows the approximate net worth in thousands of dollars of 50 small businesses. So we've got 5 classes here, and we're going to calculate the relative frequencies for each. Now you have another slide that actually has this column that you can fill these in on, but I'm going to do it here just so I'm not giving away the answers right away. Okay, so if you remember right from the other section, we've done this a couple different times. So the cumulative frequency, I'm sorry, not the cumulative frequency. We want the relative frequency. We want to take the frequency and compare it to the whole. So remember, there's a total of 50 here. So we want to take each of these values and divide it by 50. So 8 divided by 5, they show down here, or divided by 50 rather, is 0.16. So the relative frequency of the first class is 16% or 0.16. Then we're going to continue that. So 14 out of 50 is 0.28. So that's the relative frequency there. So 20 out of 50 is 0.40. So you're going to divide that, just 20 divided by 50 on your calculator. That's going to get you 0.40. And then 5 out of 50 is going to get you 0.10. And 3 out of 50 is going to get you 0.06. And so that's your relative frequencies for each of these classes. Each class has a frequency and a relative frequency where we compare that frequency to the total. How much out of the total is it? So again, they have their nice table here. And in order to graph this, we're going to have the class boundaries for the histogram. Put that up here. So we need the class boundaries for the histogram and also for the ogive. We need these, and then we need the midpoints for the frequency polygon. Okay, so they just added this here, and again, just real quick, in order to get those midpoints, we just average these two numbers. So 35.5 plus 42.5 divided by 2 gives us 39. It's the number, it's the midpoint between 35.5 and 42.5. Okay, and so here's our midpoints and our relative frequencies. So now we have everything we need to draw either the histogram, the frequency polygon, or the ogive. Well, I'll take that back. We would have to have the cumulative relative frequency before we do the ogive, but at least we have what we need for the x-axis. Okay, so without going forward to the other slides, again, I must use these to draw our graphs so that you can put it on your slides that are shown below. Okay, so we're going to have, for our histogram, remember we want to do the class boundaries. So we're going to mark our class boundaries, 35.5, 42.5, 49.5, 56.5, 63.5, and then finally 70.5. And then over here, instead of looking at what the frequencies were, so we don't care so much that our largest frequency was 20, what we care about is what our largest relative frequency is. So our largest relative frequency is our 0.4. So we need to make sure that over here, for our relative, I'm just going to put RF if you'll forgive me. Okay, so for our relative frequency here, we're going to make sure that that gets up to 0.4. So I think I'll do like I did before. I'll call this 0.10. I'll mark the one below it, but I won't label it. So that would be 0.15. This would be 0.20. So 0.20, 0.10. This is 0.30. And this is 0.40. And that's as high as we need to get because that's our highest relative frequency. And then we're going to do the histogram first. And we'll label this, what was the graph about? Net worth of businesses. Okay, so we can say down here, net worth must be in they didn't say, but it must be in 100,000, in thousands of dollars probably. And so this is the net worth, and this is small businesses. And we're going to look at our boundaries. So 35.5 to 42.5 has a relative frequency of 0.16. So right here is 0.15, so it'd be just a little bit above that. And we want to go from 35.5 to 42.5. Okay. And then we want to bar at 0.28 between the 42.5 and the 49. So 0.28, here's 0.2, 0.25, 0.28 would be just under the 0.30. And then we need 0.40 for the next one. So we're going to be all the way up here. That'll be our highest one. And then we're going to be at 10%, 0.10 for the next class. And then our final class is 6%. So here's 5%. We want to be just above that. So you can see it climbs to where a good majority, or a good number, the 0.4, good majority are in these two classes. And then it really drops off. They only have a few businesses, 10% and 6% that are above 56.5 for their value. 56.5, is that 56,000, 56 million? I don't know. Okay, so now let's do that same thing for a frequency polygon. I'm going to scooch this over because we don't need the boundaries for the frequency polygon. We only need the midpoints. So I'm going to make the same graph. And much of it's going to be the same, except for the way that we label the x-axis. Okay, so we're going to come down, over, and we still want to label the, man, that side one is hard for me to draw. Let me try again. All right, that's doable. All right, so we're going to label it up to 40% again because that's still our highest. So 10%, 0.1, 0.2, 0.3, 0.4. We can still label this side as relative frequency. And on the bottom, instead of the boundaries though, we're now going to put the midpoints. So we're going to start with our 39. Remember, we're going to have one before that though, so give yourself a little space here. So I'm going to use 39 here, and then 46, and then 53, and then 60, and finally 67. And I'm going to make the same marks or the same heights as I did over here. So for this class that went from 35.5 to 42.5, for the frequency polygon, I'm just going to get one dot at 0.16. So at the midpoint, 39.4, I'm going to get a dot. And then at the midpoint, 46, which represents 42.5 to 49.5, I get one dot at 28. And then at the 53, I'm going to get one dot at 40 to represent that class that's between 49.5 and 56.5. And then 60, I'm at 10%, and 67, I'm at 0.06. Then I connect those dots. Okay, so get those dots connected. And then again, we can't leave this just floating around up here. It's a frequency polygon. And so I need to anchor it down. And so I'm going to go, these are going by sevens. And so I'm going to go 7 back from 39 and label this as 32. And anchor that down to 32. And then I'm going to go 7 up from 67 to 74. And I'm going to anchor that at 0. So we're saying in the category that was, in the class that was before the one with the midpoint of 39, I had 0. So we're saying, you know, there was 0% or 0.00 in the category before, and there was 0 or 0.00 in the category after that, the class after that. If there had been another class, it would have been 0. And we've anchored that down then to the bottom. And again, this is still net worth, and this is still small businesses. So this is our relative frequency histogram, and this is our relative frequency polygon. So let's look at their beautiful illustrations of that. So this is what theirs looks like. And for our last type of graph, remember there were 6 types. There was the frequency for each of the histogram, frequency, polygon, and ogive, and then there was the relative frequency for each of those, making 6. So now we're going to do the cumulative relative frequency. So we already have the frequencies up here. Okay, we had the frequencies here. Wow, where are they at? They're all the way up here. So we had the frequencies up here, and then we had the relative frequencies here. Now they decided to use the method where they went through and they put the cumulative frequencies here first. And so, but again, you could calculate you could take the relative frequencies and do that. I'm going to do that method here so you can see it. So the other way to do this, instead of going back to the frequencies and doing the cumulative from there, you could also do the cumulative relative frequencies from these values. Okay, so this would be 0.16. Okay, because at that point we have 0.16 that are 42.5 or less. Then we're going to add the 0.28 to make 0.44. And then we're going to take the 0.44 and we're going to add the 0.4 to get 0.84. And then we're going to add the 0.84 to 0.10 to get 0.94. And then we're going to add 0.06 to get 1.00. So you're saying 100% of the data, or all of the data, the entire whole, is 75.5 or less. Now, if you compare that to theirs, in this situation, we do not get different numbers. We get the same numbers. But again, sometimes due to rounding, if you use one method or the other, they might be a little bit different. So now, how do we graph that? Well, we're going to take these values and we're going to use the class boundaries again, because remember, the histogram and the ogive use the class boundaries. Okay, so we're going to start with 35.5. And we're going to make that our first. Well, let's talk about the y-axis first, because we've done that for the other ones. So in this case, we need to get all the way up to 1, because that's our largest thing for our cumulative relative frequency. And so I'm just going to go by 10% each time. So this is 10, 20, 30, 40, 50, 60, 70, 80, 90, and 1. Okay, and this would be, again, I'm just going to use the letters, this would be the cumulative relative frequency. And down here, we're going to start with the 35.5. Again, give yourself a little space just in case you need it. In this case, we don't. But all right, 35.5, and then we have 42.5, and then we have 49.5, and 56.5, 63.5, and 70.5. 35.5 less than 35.5 or less, that is the lower bound for our lowest class. Okay, so our lowest boundary. So we don't have any values that are 35.5 or less. Okay, so that's our anchor point. Okay, so our anchor point is at 35.5. Okay, and then we have, oops, let's slide that over just a little bit. And then at 42.5, we have 0.16. 49.5, we had 0.44. 56.5, we have 0.84. And then 63.5, we have 0.94. And then 70.5, that's the upper boundary for the largest class, or for the highest class, and so we're at 1. That's everything, or 100% of the data. And then we're going to just connect the dots again. And again, Ogives, whether it's a cumulative relative frequency or just a cumulative frequency, Ogives can only increase or potentially stay flat if you have a class that has 0 data values in it. And small businesses. I don't want to show you guys any bad habits by leaving these things off. All right, so we are almost done with section 2.2. This is by far our longest section in chapter 2. Section 2.3 and 2.4 are both pretty short in comparison, especially 2.4. So when you do your homework, it's kind of the same way. Leave yourself plenty of time to get 2.2 done, but when you get done with 2.2, 2.3, and 2.4, you're kind of home free because they're quite a bit easier. Okay, so this is their pretty ogive for the net worth of businesses, the cumulative relative frequency. And then we're going to talk about, we have 2 slides left, 3 slides left, 4 slides left. But the last thing that we're going to talk about are the shapes of distributions. Okay, so we have distribution shapes. And we have some names for them dependent on their shape. So you may have heard, you probably have heard of like a normal curve or a bell-shaped curve. A normal curve, or close to normal curve, is also called a bell-shaped distribution. And that is when we have this kind of pattern where the graph goes up, it peaks, and then it comes back down. So the data is very much heavy in the center, and then it drops down kind of symmetrically on each side. We call that bell-shaped or approximately normal. Now, if it was exactly normal, it would be exactly symmetric on both sides and also has some other features. But bell-shaped or approximately normal is this shape that looks like a bell. You know, think of the Liberty Bell. Now, a uniform distribution, or close to uniform, in this case, is where it's more or less flat. Now, if it was exactly uniform, it would be exactly flat. Every single bar would be the same height. So this is only approximately uniform or close to uniform. But this idea of uniform meaning you just don't have a lot of variation between the classes. All the classes have almost exactly the same amount of data in each of them. Okay, so next we have what are called the J-shaped and the reverse J-shaped. So, you know, if you think of the letter J, this one right here kind of looks like a letter J. Okay, and this one looks kind of like a backwards J. So what we're saying here is that the data starts low, and then it just continues to build until your biggest class, your class with the largest values, the largest frequency, is all the way to the right. The highest class is got the largest frequency. And then a reverse J-shape is just the opposite. The first class has the most frequency, and then it just declines all the way until your final class. So that's called J-shaped, reverse J-shaped. Out of these so far, out of the 4 we've done, this one by far is going to be the one that we're going to see the most in the future. Okay, the bell-shaped. We'll see the others, but not as much. So bell-shaped is the most important out of the 4 so far. And then another term, 2 other terms that we're going to learn are what left and right skewed. It's kind of one term, the skewed. And then you just have to learn the difference between what's right skewed and left skewed. A lot of people, when they look at right skewed and left skewed, myself included when I was a student, get mixed up as to which is right and which is left. Because when you look at this curve here, you say, okay, well, the data came up. It's not like a J shape because it doesn't start high and just continue to go down. It starts a little lower, then it comes up, and then it just kind of drags out to this side. You know, just kind of keeps getting smaller and smaller and smaller. Same thing here. We have this peak here, and then it just sort of drags out. The data sort of drags out to the lower classes. Now, this one, I used to not understand. Why is this called right skewed when the bulk of the data is at the top? It's to the left of the graph. Why would that not be left skewed? Well, it's because when we're talking about skewedness, we're talking about where the data tails off. So in this case, the data tails off to the right. So if you think of it kind of as think of it as an animal, you know, a big dinosaur. This is the dinosaur's body. This is the dinosaur's tail. You know, this is the body of the dinosaur, and then this is their tail. Okay, we're talking about the tail when we're talking about which skewedness it is. So this is right skewed because it tails off to the right. Okay, let me get rid of that ugly picture I just drew. All right. But because it tails off to the right, we call that right skewed. And because this tails off to the left, we call that left skewed. Again, think of this as the body of some animal, and then this is their tail. Now, what does that mean? Well, in a right skewed graph, the reason that it tailing off to the right is important is because that tailing off to the right pulls the average, or pulls the mean. And I know we haven't talked about mean, median, and mode yet, but the mean is like the average where you just add them all up and divide. This pulls the mean up above the median. The median being just cutting the data in half the data below a point and half of the data above. So when it tails off to the right, that pulls the average, the mean, up above the median. And then for the tailing off to the left, that pulls, as you can imagine, the mean below the median. And so instead of your mean and your median being kind of close to each other, that skewedness pulls that mean down below. If you think about a bell-shaped curve, the middle of the data and the average of the data, the mean, where you just add them all up and divide by how many there are, they would both be right about here. It's kind of clear that they'd be together. But when you look at the skewed data, that doesn't hold true, because the average is going to be down here, or I'm sorry, the middle is going to be down here, but these tailing off values are going to pull the average up. So the middle is going to be down here somewhere, but the average, think about a class where, let's use this one for the class. So let's say you have a class where almost everybody in the class does well on an exam. So they're in these upper bars. Let's say they're, most of the class is up here on an exam, okay? So most of the class is up in these bars, okay? So most of the class is up here. But you have a few people who did poorly on the exam. So these people got, low scores on the exam. So you have these few people that got low. So most of the class did fine, but a few people got low scores. Well, what does that do? Even though most people in the class did fine, and you would say, over half of the class did well, then you still have these lower scores that are going to pull the class average down. So if you looked at, where most of the class was at, you would say most of the class did okay. But if you look at just the average, it might make it look like the class did poorly because those lower scores pull that average down. Okay, and that's important when we look at, when we analyze data. Okay, let me get rid of all this junk again. All right, and then finally we have bimodal and U-shaped. So bimodal, again, I know we haven't talked about mean, median, and mode, but remember mode, you probably have heard this at some point. Mode is the class with the highest frequency, or the modal class. So the modal class is the class with the highest frequency. So in this case, we have this class and this class had the highest frequency. There wasn't a single class that had the highest frequency. There were two of them. So we call that bimodal. So two classes with the modal value. Okay? And so we call that bimodal. You can also have trimodal and others. But again, this is not going to be as important. Out of all the ones we've done so far, including these two, the normal, close to normal, we put a star by already, and then the left skewed and right skewed. These are going to be the most important ones that we'll see again later. Okay, so what does U-shape mean? It's just what it says. It looks like a U. It's kind of like the reverse of a bell curve. Instead of starting low, going high, and coming back, it starts high, goes low, and then goes back up. So if you looked at it, if you can visualize looking at it upside down, the white part here would kind of look like a bell curve upside down. So it just, instead of going low, high, low, it goes high, low, high. And that's called a U-shape. And that's all we have for section 2.2. I know it's already been a really long one. Hang in there. Section 2.3 and section 2.4 are not as long at all. They're both, section 2.4 especially is really short. So we've gotten through probably 2/3, if not more, of chapter 2. Now that we're done with section 2.2, and you should be prepared to do all the homework through section 2.2, and I'll see you back for section 2.3.